ரைட். ஓகே. சரி.
ஹலோ செந்தில். ஹலோ அரவிந்த். அரவிந்த். இஸ்ரேல். ஹலோ அரவிந்த். 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 இஸ்ரேல். செந்தில். ஹலோ செந்தில்.
ஹலோ ஹலோ
கேக்குதா?
கேக்குது சார்.
நல்லா இருக்கியாப்பா?
நல்லா இருக்கேன் சார்.
Thank you very much for accepting our invitation.
Thank you சார். Thank you சார்.
அப்புறம் வைஃப் எப்படி இருக்காங்க?
எல்லாம் நல்லா இருக்காங்க சார்.
அப்படியா? இப்போ ஆஃபீஸ்ல இருக்கீங்களா?
இல்லை சார், நான் இது ஆக்சுவலாக வெளியில் போயிட்டு வந்தேன். ஸோ இங்கே ஹோம் குவாரண்டைன்.
அப்படியா? சரி 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 சரி. குழந்தைங்க நல்லா இருக்கா ரெண்டுமே? ஹலோ ஹலோ.
எல்லாம் ரெண்டு பேரும் இருக்காங்க.
கிரேட். சரி, இப்போ எங்க இருக்கீங்க வீடு?
மத்திய பிரதேஷ்ல இருக்கேன் சார்.
அப்படியா? சென்னையில இல்லையா?
ஆமாம் சார். இல்லை சார், மூவ் பண்ணிட்டேன் சார்.
அப்படியா? சரி 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 சரி. அங்க எப்படி நீங்க தனியா இருந்துக்கிறீங்களா இல்ல அம்மா கூட இருக்காங்களா?
இல்லை தனியாக தான் சார் இருக்கேன்.
அப்படியா? உன்னெல்லாம் பார்த்து ரொம்ப நாள் ஆச்சுப்பா. சான்ஸ் கிடைச்சா அப்படி வாங்க. ரைட்டா?
கண்டிப்பாக சார், கண்டிப்பாக.
வந்தா நம்ம பார்ப்போம் ஷூரா. அப்புறம் ஃப்ரெண்ட்ஸ் எல்லாம் எப்படி இருக்காங்க?
எல்லாரும் நல்லா இருக்காங்க சார்.
கான்டாக்ட்ல இருக்கானுங்களா?
எல்லாருமே ஆல்மோஸ்ட் எல்லாருமே கான்டாக்ட்ல தான் சார் இருக்காங்க.
Very good, very good. I really am very happy that you have grown up like anything. And also you did
Thank you,
us.
sir.
Really, I feel very happy about that. Where you did it
Sir.
was?
Bits Pilani, sir.
Oh, great, great, great. Very good, ma. சரி இப்போ ஆல்மோஸ்ட் ஆரம்பிக்கும் போது ரைட்டா
Okay, sir.
பாருங்க 1 hour இல்லையா பார்த்துட்டு end of this webinar we will talk, right? Because all the
Okay, sir.
participants
Sure.
are not entering. Okay.
Sure.
All that is, thank you so much, ma.
Sure, sir.
Okay, pa. Right.
இதில் ப்ரெசன்டேஷன் எப்படி சார் பண்ணுறது?
ப்ரெசன்டேஷன் உங்களுக்கு இப்போ ஸ்லைட்ஸ் வச்சிருக்கீங்களா?
வச்சிருக்கேன் சார்.
நான் ஒரு ஹோஸ்ட் பண்றவர் இஸ்ரேல் இருப்பாரு, அவருக்கு நம்ம ஷேர் பண்ணிட்டா அவர் வந்து பாப்பாரு. இல்ல நீங்களே கூட பண்ணலாம், அவரை பேச சொல்றேன் நான், ரைட்டா?
ஓகே சார். ஷூர்.
ஓகே ஓகே. இஸ்ரேல் இஸ் தேர். இஸ்ரேல் இஸ்ரேல் அரவிந்த்.
மிஸ்டர் சந்தீப் சார் கேக்குதுங்களா?
கேக்குது.
ஓகே சார், உங்களுக்கு பிபிடி ரெடியா இருக்குங்களா?
ரெடியா இருக்கு.
அவங்க ஷேர் ஸ்கிரீன் கிரீன் கலர்ல தெரியுதா சார் கீழே?
ஆமா. எஸ்.
விண்டோ பாட்டம்ல
தெரியுது.
நீங்க அதை கிளிக் பண்ணி ஷேர் பண்ணுங்க சார். எஸ் சார், உங்க ஸ்கிரீன் தெரியுது தெளிவா?
தெரியுது.
யா, நவ இட்ஸ் ஓகே. யா, ஃபுல் ஸ்கிரீன். ஓகே, ஷூர். குட். சோ இந்த வீடியோ போடுறீங்களா சார் நீங்க?
வீடியோ வேணானா ஆஃப் பண்ணிடுறேன்.
இல்ல ஆக்சுவலி ஐ அம் ஆஸ்கிங் whether you going to put any video on the screen?
Yeah, it will be
to the participant.
Yes.
Can கொஞ்சம் போட்டு பாத்துங்க சார், ஒரு தடவை செக் பண்ணிடலாம்.
Sure. வீடியோ ப்ளே ஆகுதா?
இல்ல சார், எதுவுமே ப்ளே ஆகல இன்னும். உங்க ஸ்கிரீன்ல ப்ளே ஆகுதுங்களா?
என் ஸ்கிரீன்ல ப்ளே ஆகுது. மேபி ஐ ஹேவ் டு ஷேர் தி ஸ்கிரீன்.
Yeah, you can share the screen itself then.
Fine.
Instead of PPT.
Fine. So still you can see my presentation alone, right?
Yeah, that we can able to see that.
Fine. Yeah, just let me know when we can start this presentation.
Just a minute, sir. Actually,
Oh,
Shiba Mama
fine.
has to come.
Okay.
After a few minutes, you can switch off your video, sir. Okay. So after
Sure.
starting this session. Sure.
Sure. Sure.
Instead have come.
Oh, okay,
So,
ma'am. You can decide whether we can start it now or not.
yeah, only 64 participants. We'll wait for 10 minutes to start. Hello, Central Kumar. This is Sheba.
Hello. Hello.
I'm your senior. Hope you remember.
Yeah, I remember you.
Yeah. How are you?
Yeah, I'm fine. How are you?
Yeah. How is Annapurni?
Yeah, she's fine.
Yeah. Okay. Convey my regards to her.
Yeah, sure.
Hope you're comfortable with all your screen sharing, everything, right?
Yeah, I'm okay. Fine.
I'll check with the students also. Reshma, are you there? Reshma.
Yes, ma'am. Yes, ma'am.
Okay. Your mic is okay, right?
Oh, yes, ma'am.
Yeah. Be slow and reading, right? Okay.
Okay, ma'am.
Okay. Shalini.
Yes, ma'am.
Yeah. Okay. Okay. You're comfortable, right? Be slow and reading. That's all, right? Mic is okay. Yeah.
Shiba, I'm also present.
Okay, sir. SPCT chemical name இருக்கீங்களா?
நானாப்பா இல்ல என்னோட இதுல லாகின்ல தான் இருக்கேன்.
ஓகே தெரியல இருக்கு. ஓகே சார். செந்தில்
தெரியலையா?
குமார். இப்ப தெரியுது. கீழ எனக்கு தெரியல சார். அது.
ஓகே.
ஓகே சார்.
செந்திலுக்கு நீங்க சீனியரா ஜூனியரா?
நான் சீனியர் சார்.
சீனியர்.
எத்தனை பேட்ச்?
எனக்கு அடுத்த பேட்ச் செந்தில்.
அப்படியா? கிரேட். சிவா டைம் மேனேஜ்மென்ட் பண்ணிக்கோ புரியுதா?
ஓகே சார். Bilal, are you there?
Yes, ma'am.
Bilal is there.
Yeah. Bilal, mic கொஞ்சம் கிட்ட வச்சு பேசணும் சரியா? Yeah,
ma'am. Okay.
Senthil Kumar, actually,
Yes.
your starting would be welcome address, followed by introduction of the chief guest by the students, then your session, then will be queries, and then vote of thanks.
So am I audible?
Yeah, you are audible. Yeah. Sir, when shall we start, sir? We'll wait for some more minutes. We have 79 participants here.
You have to tell that, okay, whether that participant is yet to come or not, right? Suppose only...
They're coming inside.
And also
maybe...
we cannot wait for a long time, okay?
Yeah, yes, sir. 5 minutes, sir.
Okay, you have to get a permission from Sandil sir, okay?
Yeah, yes, sir.
Yeah.
Is it okay, Sandil?
Yeah, no.
Can wait for 5 minutes?
Yeah, no problem.
Yeah.
Shiba madam. Hello, Shiba. Shiba madam.
Yes, sir. Yes, sir. Shall
I
we
think
start?
we can start. Yeah, ma.
Yeah,
We
yes,
can start, ma.
sir.
Okay.
Okay.
Yeah.
Good morning, one and all present here. We all welcome you all to the Chemical Engineering Learnathon Day 2 session. I request Reshma of third year to deliver the welcome address. Reshma? 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 Reshma?
She is not in the participant list, ma'am.
I think she has gone. Yeah, okay. Good morning to one and all present here. Hope everyone are fine. Everyone are fine. We welcome you all to the Chemical Engineering Learnathon 2020, jointly organized by the Department of Chemical Engineering and IICIT Student Chapter SPCT. This is a webinar delivered, which is going to be delivered by alumni Mr. D. Sendil Kumar, a honorable speaker for this session. On behalf of our management principal, I would like to extend a warm welcome you, sir, who has accepted an invitation and going to share our thoughts on latest trends in grinding technology. I cordially welcome our beloved HOD, Dr. S. Dinesh Kumar, sir, for being such a supporter for each and every step taken by the department staff. I would like to welcome our coordinators, organizers, and staff members for this event. Last but not the least, I would like to extend my heartfelt welcome to all the participants across the country in joining this session. I welcome you once again. I welcome you all for this session. Now I request Shalini of final year to introduce our chief guest.
Good morning, everyone. It's my pleasure to welcome Mr. D. Sendil Kumaran, Senior Manager in Heidelberg Cement India Limited. He has more than 12 years of experience in operation, maintenance, commissioning, and troubleshooting. He has completed BTech Chemical Engineering and MS in Manufacturing Management. He has previously worked as commissioning engineer and manager in various projects in India, China, USA, Brazil, UAE, and Jamaica. He also successfully commissioned pyro system in 8 major projects. He also worked as a senior process trainer in USA. He also commissioned in the world's largest hot disk in USA, commissioned to alkali bypass system. His work involved in RTO, pollution and emission controlling equipment, and also optimized alternative waste firing in 3 projects and pet coke grinding and firing in 5 projects. So I am very glad to welcome our alumni, Mr. D. Sendil Kumaran, to take over the session.
Good morning, everyone. Am I audible?
Audible.
Okay. Okay. So, good morning. Myself, she introduced me already. My name is Sendil Kumaran, and I'm working as a senior manager in Heidelberg Cement India Limited. So today, let's go to the session. We'll see about the latest trends in the grinding technology. In this slide, behind this, I'm standing in front of a big mill, which is a vertical roller mill, and I'm standing along with a few of my Chinese friends. So this is that's how the mills will be. So we'll go to the session. So this is done. So basically we'll see about a typical cement plant flow sheets. Basically it starts with the quarrying, and from the quarrying the main ingredient is limestone, and then the clay, sand, and iron ore. They all sent to the crusher, and from the crusher it's been stored, sent for the storage, and from the storage it will be sent for a raw mill, and then it will be stored in a silo, and then this is a pyro process. From the pyro process, it will be cooled down, and the product will be called as clinker. The clinker, along with the gypsum and other additives, will be grounded once again, and that's called as a cement mill. And then the product is same stored in a silo, and then it will be sent to the packers. So this is a typical cement plant flow sheets, out of which we are seeing a lot of size reductions and the grinding operations here. It starts with the crushing activity in the first step, and then it is the milling operation, and then there is one more cold mill operation here, and then here cement mill operation. So here the size reduction plays a major role in the cement plant operation. So let's see about the size reduction process here. So why do we need to grind and dry? Basically, like when we reduce the size, we are increasing the surface area of the material. So as we can see the pyro process, is like from as the name indicates, we have to fire the fuel and heat it up. So when we want to optimize the fuel consumptions, so we have to increase the surface area so that the process completes easily and without much issues. So to make a perfect cement, so we have to optimize our cost in terms of fuel consumption as well as the power consumptions. So that's main reason why we are grinding and drying. So, and also for a streamlined process, it's like these are all continuous process what we are talking about. So for the continuous process, the product or the feed should be homogenized. It should be uniform enough so that the fuel variations and the power variations will be streamlined. So to optimize that, we need to grind and dry it, and for a better heat transfer in the pyro system. So when we see the power split in the cement plant, so only 33% of the power is spent in the pyro operation, and 2% in the packing plant, and 2% for the crushing. Major 63% is due to the grinding. So that's why the grinding operation is so important, that we have to optimize it and we have to choose a proper solution for the grinding. So here when we see crushing of the raw material, it takes 1 to 2 kilowatt hour per ton of clinker. Grinding of raw meal, it takes 10 to 15 kilowatt hour ton of clinker. For cold grinding, it is 2 to 4. For cement grinding, it is 30 to 60. So total comminution grinding alone, it's 45 to 80 kilowatt hour per ton of clinker. So crushing, when we see about the crushing, the size reduction, it reduces the size from above 1 meter of rock, it reduces up to 25 to 100 mm. But the power consumption is only 0.2 to 1 kilowatt hour per metric ton. For the raw grinding, the size reduction is the 25 mm particle we reduce up to 85% less than 90 micron C. The energy consumption is around less than 20 kilowatt hour per metric ton. Where in the finished grinding, the same 25 mm clinker, we reduce to 95% less than 45 micron C, where the power consumption is 26 to 45 kilowatt hour per metric ton. Even though the crushing, it reduces when we see the band, the major band is the crushing. So that's like from 1000 mm, it reduces to 25 mm. But the power consumption is less. But wherein when we go down, the raw grinding, it consumes more power. And in the finish grinding, it consumes even more power. The reason is the fineness level. As we increase the fineness level, the power consumption increases. Like for example, if we have a small rock and we are blowing it up with a hammer, this within one or two blows, that rock size will reduce to 2 or 3 pieces. But if we want to make that rock to a fine powder, then we have to keep on hitting it. At least it will take 25 or 30 blows to make it into a powder. So that's we can relate it with the power consumption. So the more finer we grind, the more power it consumes. So that's the reason why the raw grinding and finish grinding power are on higher side. So when we see this raw grinding here, from 25 mm, we are reducing to 85 percentage passing on 90 micron. And for the finish grinding, 95 percentage passing on 45 micron. So it is ultra fine product. The cement, as we all know, it's a very ultra fine product. So that's why the power consumption is on higher side. So when we see the principles of size reductions, they are impact, compression, attrition, and shear. So these are the major 4 principles of size reduction. So wherein the impact, when we see the impact, so it is a quick, sharp blow which causes the stone to shatter. So this is a typical industrial crusher. It works on the same principle. This equipment, particular piece of equipment is called single rotor blow bar crusher. So this works on the principles. This rotates in a very high speed, and then it passes the material. Here above this, there will be the impactors. The blow bars hit the material and it hits on the impactor, and then it reduces the size. Below this, it's called as the grizzly bars. So this, based on this setting, the size reduces. So this is an impact. And here we see about the compression. Compression, this is a simple bench press. And here it is the jaw crusher. Jaw crusher, it is one of compressing equipment. So there will be like a fixed end, and this is a movable end. So when the stone is slowly compressed to a breaking point, it suddenly shatters. Jaw crusher and cone crushers make use of the compression principle. Then we see about the attrition. Attrition is a saw, works like a saw. So when the stone is worn down by continuous abrasion, this occurs between the grinding media and the ball mill. This is a typical industrial ball mill. It is much bigger than the ball mill we have in our lab setup. So here the balls, it is, this ball mill is typically 2-compartment ball mill. So here the first compartment is having a higher sized balls, like 90 mm to 60 mm media. The grinding balls will be there. And then the second compartment will be for fine grinding. The fine grinding will be where the ball size will be typically between 25 to 15 mm. So this will be having a very fine sized balls. So then the shear forces. Stone can be cut by applying the off-center forces in opposite directions. These two rollers with the sizing tooths, they rotate in opposite directions, and then it acts like a crusher, like a scissors or shears. So this tooth roller crusher make use of the shear principles. So this, where the compression and the impact will have the lower energy and lowest wear, wherein the attrition the wear and the energy consumption will be of higher size, because the impact, the fineness cannot be achieved, and then the attrition, the fines can be achieved. So the compressed, we'll see about three major equipments, or the three major machineries for grinding today. Is first is ball mill, and then we'll discuss about the vertical roller mill, and then the roller press. So this in the top, it is the roller press. You can see someone raised a hand. Yes. Mr. Vijay R. Hello. Hello. Am I
Yeah, we
audible?
can yeah, you're audible.
Yeah, I see someone has raised a hand.
They may not be knowing, I think.
Okay. Shall I proceed?
Yeah, you can proceed.
Okay, fine. So the common grinding machines in cement plant, we'll see about these three grinding machines: ball mill, vertical roller mill, and the hydraulic roller press. So we'll see about these three machines. First is ball mill. So this we have seen already. So this is grinding operation in a ball mill. This is a 3D view of a ball mill. So without the balls, of course. So this is the first one is the first compartment, and then this is the second compartment. First compartment is majorly for coarse grinding, and second compartment is for the fine grinding. So this here the mill from the one, the material enters from this side and then leaves from the other end. So the coarse material enters inside, and then the fine product goes outside. That's how this works. So the grinding process, the first compartment is grinding by impact. Like as I said, the higher size grinding media, like the 90 media or 80, 70, 60. So these balls on impact, it breaks the particles by ball's impact due to falling. So the ball mill rotates, and then the ball will be lifted up to some level, and then the lifted ball falls on the material, and it impacts, and it reduces the size. And then this, after some size reduction, it passes to the second compartment, wherein the efficient grinding is done by attrition. So like as I said, the small size media, like from 25 to 15 size media, they rubs along with each other, and the material passes through attrition. This ultra fine grinding or the fine grinding occurs, and it grinds the material into a finer product. So this, when we see, uh, we have studied about this principles of the ball mill, like the gravitational force acts on this due to the rotation, the gravitational force and the centrifugal force. When it equals, that's what we call as we know, uh, we must remember about this equation: 42.3 divided by root of d naught. So the gravitational force, when the gravitational force equals the centrifugal force, what happens? So as we know, if we keep some water in a small bucket, and when we start to rotate our hand in a fast manner, the water will not fall down. So after, at a slower speed, the water will fall down. So that is called uh, critical speed. So when the gravitational force equals the centrifugal force, so the media, it is a rotating equipment, and the media is on the, we fill the media up to 30% in this mill. So when it rotates, if we are rotating in a critical speed, all the balls will stuck to the walls of the ball mill, and the ball will not fall down. The ball will not fall down, and then the impact or the attrition will not happen. So the effective grindings will not happen. So what happens is, so typically when we design this ball mill, we choose up to 77 or 78 percentage of the critical speed. So that's the point where the effective grinding occurs. As we can see here, so when the ball rotates, this is rotating in a clockwise direction. So the release point 1, where if the ball released from this point 1, it cascades, and the second point where the max impacts will be there. And if it is in the third point, if it is lifted up to the third point, it impacts on the liners. As you can see, we discussed about this, the ball, the 90 mm ball. So when it is hitting on the shell, it will damage. So the life will not be that much. So what we do is, here when we see this yellow portion, it is all lined with the liners for protection. And for this first compartment, since it's a bigger size media, the impact will be more. For protecting this, the bigger size step liners were installed. And in the second compartment, where the impact is lower, uh, corrugated liners were placed here. So we'll see about this. So when the media directly hits the liners damage, and the wear will be higher and the breakage will be higher. So that we don't want that to happen to the third point. So that's how the percentage of the critical speed is chosen. So the energy transmitted in the balls, mass based on the ball sizes and the specific weight, speed, movement, mill speed, filling, and liners. So these are the impacts. These are the major factors which will implement on which will affect on the grinding process. So this is a typical ball mill. So this we have seen already. So this is the liner. The first liner, first compartment, the liners will be like the stepped ones, and then the second compartment, it will have corrugated liners. So this is the central diaphragm and ventilation ring. So through this, the material passes and it passes to the second compartment. And then here, these are the coarse balls, and this is the fine balls. This is how it typically looks. We fill only up to this 30% of the mill volume. So this we have discussed about that. So critical speed is the speed where the centrifugal force at the mill lining is equal to the gravitational force. Critical speed equation is 42.3 divided by root of d naught. So the normal mill speeds are 75 to 77% of the critical speed. So this, can we see here, these are the different, on the y-axis, the ball charges in percentage of the mill volume, 10%, 20%, 30%, and 40%. And on the x-axis, the movement of grinding media and tube mills, like 20% of the critical speed, 40% of the critical speed, 60% of the critical speed, 70%, 80, and 90%. Then we'll see from the top, at lower filling level, 10%, at lower and lower critical speed, the ball won't even lift. So here, the grinding will not happen. And here, when we see here, at lower filling, the effective, and this, we are not seeing any impact over here. So lower filling is also not recommended. And at 20%, when we see between the 70 to 80, where we target, so the impact is happened, but not up to the mark. So when we see about the 30%, we can see this, the mill rotates, the media lifts up, and it is effectively falling in the charge. So the effective grinding occurs in between this area, between the 70 to 80. So based on the experience and the different liners and the different suppliers, the percentage of the critical speed is chosen. So this is mill charge. So typically the charge will be of 30% of the mills. So I can see someone else raise the hand. You can ask the question. Hello. Is there any questions?
Uh, if anybody wants to question, you can put it in your chat box. Okay? If you want to ask questions, you can put it in your chat box. You can continue.
Okay. Let me continue. So we'll see about this the ball mill we have seen, and then we'll see about the vertical roller mill. As here we can see this vertical mill. So let me share a video of this vertical mill. So this vertical mill is like almost like our wet grinder. We'll have 3 rollers, and this is a center yoke, and it's a table. The table rotates. So due to the rotation of the table, the rollers also rotates, and it forms a bed between the table and the roller. And then the effective bed, we use water for stabilizing the bed, and then the bed stabilizes, we grind the final product. So this is a vertical roller mill, typical mill. Maybe I can share a video on this animated video. So is everyone able to see the video?
Yeah, we can see.
Okay. Yeah, I am starting the video now. So the feed enters. So this is a vertical mill. So the feed enters inside the mill, and this is a table, and then the feed enters inside. So this tube, what we are seeing here is a water spray. So we spray the water to stabilize the bed, and then due to the rotation of the table, the rollers also rotates, and then the metal get finely grounded and lifted up. So this is how the rotation will be. So the roller, it compresses the material, and then it grounds the material. So here, what we see here, this is a dam ring. So it acts like a dam, and it keeps the material bed up to this level, so that the stable bed will be maintained. And then, so here when we see here, this is called nozzle. The hot air passes through this, and it dries the material and lifts it up, and it moves to the separator. So we'll see about the separator soon. So the finely grounded material, it passes above, and it goes to the separator. This is separator. What it does is, like, as we see, the requirement is a finely grounded material. So due to this, it separates the material, the finely grounded material above this, and collects to the products, and then the coarse products will be returned back due to this rotation action. So the coarsely grounded material comes back through this chute, and it recirculates again to the system, and it grounds finely grounded again. So the material, the sum of the material which escapes, it is recirculated back. This is a bell conveyor, and this is a bucket elevator. So through the bell conveyor and the bucket elevator, it recirculates back, and the material get recirculated back, and we can see that. Just a minute. So, can you able to see this screen now?
You're able to see the screen.
Okay. So process animated video. So this is how the vertical mill works. So when we see this, the presentation is visible now, madam?
Yeah, it's visible.
Okay. So this is, imagine this as a roller, and this is a grinding bed. The H here refers to the bed. So the roller rotates and the table rotates, and the material get compressed between these rollers, and then the gripping and the compression begins. So the grinding system designs, what we consider is basically the material grindability, type of process, feed size, moisture content, and then the product fineness. So we'll see one by one. Grindability, we all know about the three losses of the comminution: Hicks law, Rittinger's law, and the Bond's law. So the grindability is based on the different materials. For example, the limestone will have a different grindability, clinker will have a different grindability, and coal will have a different grindability, and the other material like iron ore or laterite or bauxite, any ores will have a different grindability. So the grindability chooses, like if the material is hard to grind, then the capacity and then the other wear materials will be chosen. So the material will be chosen, like the mills, and then the internals of the mills will be chosen based on the grindability. The capacity is all decided by the grindability process. And then the type of process, in the sense like when the process will have different materials. When we have a hot gas available, or if the hot gases is not available, and then the feed size, the moisture content. Moisture content is an important parameter. If the moisture is on higher side, so then we need a higher, hot air availability. More amount of hot air is required for that purpose. And then if the moisture is lower, then we may not need that much of hot air availability. And then the product fineness. So what is the quality of the material? What is the fineness of the material we need? So that defines the capacity and then the requirement. So the grindability is the mill power divided by the production. So this is influenced by the material components, product fineness, grinding system, and equipment efficiency. So when we come to this grinding system part, so we have seen about the material components. So if the material is hard to grind, then the grindability will be on higher side. And then the product fineness. If we grind the material more finer, then our power consumption will be on higher side. So that also we know. And then what is about the grinding system? Like we have seen about the ball mills. And then here we are seeing about the vertical roller mills. So these are different grinding system. And then there is a roller press. So they are three different types of grinding system. Wherein when we see this, ball mill consumes much higher power than that of the vertical roller mill and of the roller press. Because here the ball mill, when we see, the whole mill rotates, and the weight of the balls and the material, it has to carry away all those materials and all those weight, and it generates more heat. Most of the energy we spend for the ball mill will be used for the generating the heat, which we may not need. So the efficiency wise, the ball mill is lower efficient than the vertical grinding. So typically, when a ball mill consumes 100 kilowatt, the vertical mill consumes only 55 kilowatt. That is, the vertical roller mills are 45% more energy efficient than the ball mill. So that's why in the newer generations, the newer installations, people prefer more vertical mills or the roller presses than that of the ball mill. So we'll see about this three comparison of these three grinding systems in detail soon. So the basically then the equipment efficiency. So the efficiency of the grinding circuit, the efficiency of the separation circuit. So that also defines the grindability. So basically grindability means resistance against comminution. It is how difficult it would be to grind the specific material to the required particle size. So we'll see this one. We have seen about that. So the grinding is done through compression and shear in the vertical roller mills, and it is highly energy efficient. So the three main ways of expressing grindability in cement industry are bond work index, hard groove grindability index. This hard groove grindability index we use mainly for the cold grinding, and specific power consumption of existing mill operation and clinker grindability. So these are the main ways of expressing the grindability. So is there any questions?
Yeah, Prem Kumar has asked
Yes.
how you will control heat loss in ball mill.
Heat losses, basically when we see about the ball mill, when we put more media, the more heat will be generated. So the heat losses we can control, like we need to control the product temperature as well. So what we do is we add water spray to the system. We have a inlet and as well as the outlet water spray control. So the water spray controls the temperature, and then the losses can be controlled by adding the appropriate grinding media sizes. Like when we see the first compartment, for example, we add 90 mm, 80 mm, 60 mm, 70 mm, and this like 4 or 5 sizes of grinding media. So it depends on like how much percentage you add to each. For example, like we cannot add 100% 90 mm media. So we test the material basically. For example, if it is a limestone grinding, so the limestone will have a certain grindability. So we know this, we test this grindability and we know the value. So we don't need that much of impact force to the system. So when we have the 90 mm media, if it is keep on hitting, so only the impact will be there. The attrition will not be there. So through the proper size distribution of the medias, for example, if I would like to, normally I would like to add 23% of the 90 mm, and then 32% of the 70 mm, and then the percentage will be like that. So the proper grinding media distribution, the size distribution, that plays a major role in controlling the grinding heat losses, and also the material. So the material, when we have a material, moist material, we need heat in that cases. So it's a matter of optimizing what we would like to optimize, the hot air or the heat generation due to the grinding media. So that's how it's practically we do it. Is it clear now?
Okay. Another question. What is the cost difference between vertical grinder and ball mill?
It'll be like when we see the comparison of the cost, ball mills are pretty cheap, cheaper than the vertical mills because of the simplicities, first of all. So the grinding media, it's a simple shell, and then the gear arrangement and the separator arrangement. So it is the initial cost will be lower for the ball mill, wherein the vertical mill, the initial cost will be slightly higher. It is on higher side, vertical mills. For example,
One more question. Tell us about the centerless grinding and its advancement.
come again, madam.
Tell us about centerless grinding and its advancement.
centralized in the sense? I'm not getting it clear.
Chidambaram has asked question. Can you define the question more? Chidambaram? Chidambaram is there. Okay, can continue, Mr. Sandil Kumar.
Okay.
We'll later on come to the question.
Okay. So the is the slide away? Can you able to see the slide now?
Yeah, I can see the slide.
Okay. So the grinding of raw material, when we see, so here we have 3 or 4 types of material. It has to be ground, and it will be ground using the mill, and then it will be stored in the silo one or in the different silos. So this is a typical raw mill flow sheet. So these are all bins, and weighed all this quantity, everything we monitor, and we weigh it, and then we feed to the mill. And through this one, and this is when we see this the small this small arrangement. This is a metal detector. If there is any metal inside this system, so it separates, it detects the metal, and it separates out, and it will be taken out through reject. Because when we see here, the roller and the table will be having a material, and it will be having a contact. So when we have a metal inside the system, it disturbs operation, and in case of coal mill, it generates the spark, and it even causes explosions. So we don't want to have any metal entry inside the mill. So this is a metal detector, and through the metal detector, it separates it. There is a gate, and it separates the metal, and only the feed enter inside the mill. And then this is a external recirculation system. There will be a belt conveyor and a bucket elevator. It recirculates the material, and then the fine product collects through the product cyclones, and then it is conveyed to through the product transport. This is a hot gas system, the hot gas entry to the system. So here the system, this is a typical vertical roller mill. So drying, it can grind, it can dry up to max 8%. Size reduction, it can reduce up to 200 mm to 15% retention on 19 micron. So this is more energy efficient. Capacity is also uh, the vertical mills. The capacity can be higher as 750 metric tons per hour, and in India, one place we have 900 metric tons per hour mills also. So this can dry the material, and it is a simple layout, separator integral to the mill. So this is a typical raw grinding system. So this we have seen already. So this is the mill internal. So maybe I can show you the actual mill. Just a minute. I can show the video of an actual mill. Can you able to see the video now?
Yeah, we can able to see the video.
Okay, this is an actual video of a mill or mill circuit, vertical mill. So this is how this is an empty mill. So this is a table, and this is the water arrangement for stabilizing the mill, and this is a dam ring. So this is actual video taken for during trial purpose. So there will be the roller will not rotate at this time because there is no contact. The roller will be slightly lifted up. When the material enters, the material acts will make a bed between the table and the roller, and then the roller starts to rolling also. So this is an actual video of the mill system. So then we'll go back to the presentation. So this is can you see the presentation now?
Yeah, I can see the presentation. Yeah.
This is the table. This is a table, roller, water lines. This is air guide cone, and then these are all the nozzle rings. So this is the internal of the mill. So this is the mill external. This is the recirculation system of the mill. So there are many suppliers for the raw mill, the mill. One is FLS, one is Policius, Pfeiffer, and Loche. They are different suppliers. So everyone having their own specifications for the mill. So this grinding pressure, this defines the total pressing force and the roller dia and the roller width. So these are all different suppliers having their own norms. So this is the dam ring. So this is the dam ring height defines the how this will be taken as a trial or the optimizing parameters. These are all. So we decide the size of the dam ring based on the grinding system. So if the dam ring is height is too high, if we keep it too high, then the bed depth increases, then inefficient grinding, and it increases the power consumption as well. So if we keep too low dam ring, then the low bed depth, then the high vibration and high external recirculating load. So as we know, this looks like our wet grinder. So if we have like more material in the system, or if we don't add sufficient water to the system, then if we keep on rotating, what will happen? The wet grinder will start to jump due to vibrations, right? So it is the same. So this is such a massive equipment, such a massive machinery. So when we don't maintain any parameter properly, for example, like if the bed is not stable, if the water we are not pouring well, so if the material is not coming, or if there is any issues with the roller or the table, so ultimately what happens here is it starts to vibrate a lot. So we install vibration sensors to know this, and then we control the vibrations. So this is how the mill operation. Then the new feed enters through the mill, and then it goes to the table. It grounds well, and then some particles, 10 to 25% of the material, escapes through the above the dam ring, and it goes to the recirculation. And then the finely grounded material goes to the separator, and then the fine product goes to the cyclones, and then the coarse product returned back for recirculation. So this is how the mill operation is. So this we have seen in the video as well. So the stable operation parameters are feed size, feed to mill, hydraulic pressure, liners, water spray, false air, gas flow, separation, and instrumentations. Then it is a cold grinding VR. So we grind the raw material. Raw material is limestone powder. Limestone powder is typically a inert material, so not an issue. For the cold grinding, when we grind the coal finer, when we heat it up too much, so then the chances of explosions are high. So the basic difference between the cold grinding VRM and the raw grinding VRM is the safety precautions will be much more in the cold grinding system. So we have to ensure the safety of the system as well. So that's more important. Then for the safety, we monitor temperature, CO levels more in the system, and then we regulate the system with the inert dust materials, and we follow more precautions in the grinding system. And then there won't be any external recirculation, and only single fan will be there. So this is a basic difference between the raw mill and the cold mill. So this is the vertical mills. So due to the time constraint, I'll go for the. Then here we see about the third grinding system, hydraulic roller press systems. So this is a view of a hydraulic roller press system. So the operating principle is the communication happens between the two rollers, rotates in a different direction, and then the material fed between, and then the gap through this gap, the material is getting compressed and it forms a bed inside, and then the roller press forms a cake. So we won't get a fine product outside the roller press, and then the cake forms below this, and then the cake will be later on deagglomerated by a deagglomerators. We have deagglomerators installed in the system, and that deagglomerates the material, and then it goes to the separator and it separates. So these hydraulic roller press systems, the hydraulic force is applied between the roller press, and then it starts compression, and it breaks the material into fine particles like micro cracking. It forms a micro cracking, and it reduces the sizes. The typical specific grinding force happens is the VRM is 600 to 800. For the cement grinding, it is 1000 to 1100, and then the HRP, the hydraulic roller press, is 5500 to 6600. So this is a different circuits. Here there are three types of circuits for the roller press. First, this is pre-grinder system. So this is a single pass. It reduces the size, and then it goes to the typical ball mill, and then it is a typical circuit. It is simple. This mainly they use for upgradation of the existing ball mill system, that they use it. And then this is a semi-finished grinding system. This is also an upgradation, and the payback is higher. So the roller press have a the separate circulation system, and then the material goes to the system again. There will be a two-stage separator here. So this is a semi-finishing grinding circuit, and then there is a finished grinding. That is like there won't be any ball mill in the system. The only grinding machine is the roller press, and it is having a lower power consumption as well. So this is a typical hydraulic roller press. So this is a motor arrangement. One is fixed, this is movable, and this is fixed roller. So the feed enters through this, and it it get grounded between the rollers, and it forms a cake and goes down. So this is a hydraulic roller press system. This is a 3D view of it. So this is called as the cheek plate. Just like our cheeks, it helps the material bypassing the system. Since we are applying high pressure between the rollers, so the chances of material escaping is more. So this cheek plate act like our cheeks, and it holds the material, and it makes the grinding more efficient. So we'll see about this comparison of between these three grinding machineries. So the cost is a major part. When we see the cost of this, the ball mill will be the initial capital cost will be on lower side, and then the vertical roller press, the vertical roller mill, and the hydraulic roller press, the initial cost or the capital cost will be on higher side. Then the civil cost also, other than the machinery cost, civil cost, then the operating cost, that also plays a major role. Then the civil cost for the ball mill is again lower side, but the vertical roller mill and the hydraulic roller press, they are on higher side. And then the operating cost. Operating cost of the ball mill is on much higher side because of the higher power consumption. Then the vertical roller press and the hydraulic roller press, sorry, vertical roller mill and the hydraulic roller press, they will be on par, the operating cost. And the performance, we need same performance in all three machines. So there won't be any compromise on the final product quality. So this three machines. And then the major advantage of the roller press is roller press don't need any water spray system for efficient grinding. Wherein the ball mill, we need water spray system for cooling it down. In a vertical roller mill, we need water spray for stabilizing the bed. But for the hydraulic roller press, the water spray is not required. So in Gulf regions where there is more water scarcity, so they prefer hydraulic roller press systems more than the vertical roller mills. And there are the layout constraints and many other factors which plays a major role in choosing between these three machines. So is there any questions on this part?
Actually, they have asked if there is any surface deterioration takes place on the roller. If it occurs, how to handle that situation, how it affects the grinding efficiency.
Yes, it's a good question, of course. So the wear and tear, when we see about the wear and tear, it is common in all these three machineries. For example, in ball mills, the wear materials are the grinding media and the liners. The grinding media, if it is, for example, if I put a 90 mm media inside the mill, after some time, it will reduce to 80 mm media. Then the 80 mm media will become 70 mm, 70 become 60, 60 become 50. The 50 will perform as a, will not perform. And then the 90 has to do the impact job. That will not happen. So what will happen is the wear rate, when we are based on the wear, what we do is we top up the media. We add more grinding media to the system. For example, I measure the wear as 40 grams per ton of material, like a raw material or a cement. So I know the value, like based on the experience and based on the several measurements, I get the value as 40 grams per ton. So I know after 1 month or 2 or 3 months, the performance will not be the same like a new one. So I know the established value as the wear rate. So then I add top up media to them, like 90 mm media. The 90 mm media become to 80 mm. Then I have to add the 90 mm. After some time, like for a year, then the small size media will be on higher side. So which we don't need. So in that case, what we do is we regrade the mill. We take all the medias outside, we regrade it, we sort it out using the sorting machines, and then we sort the media and then top up after some time. So this also, the wear rate is also depends on the several factors. Grindability is one fact. If I'm getting a different material which grinds, which is wear rate is more than the normal one, then the media wear will be on higher side. And then if I have a higher moisture material come inside, then also my wear rate will go up. So they are my known factors. So based on that, the regradation or the top up we decide. And then for the liners, we go for a periodic inspections inside the mill, and we measure the thickness, and then we check it, and then we replace the liners after 3 or 4 or 5 years. So that's for the ball mill. So when the wear rate is on higher side, if we don't top up properly, if we don't replace it on time, what happens is the performance reduces. Performance in the sense, the production. The production reduces and the power consumption start to increase, and our fineness is targeted. Like we need certain quality parameter, like a finance is a quality parameter here. We will not compromise anything on the quality. So for I need the 15% retention on the 90 micron, then what I have to do? I have to reduce the production. And for reduced production within the same mill, then my power consumption, the specific power consumption increases. So then the performance deteriorates. So we have to evaluate and top up and replace and regrade accordingly. That's for the ball mill. For the vertical roller mill, the liners, the roller liners and the table liners, they they will be having like if it is worn out. So for example, if the table worn out, the table liners getting worn out, then my dam ring will be, the height will increase naturally because my the depth of the table liner got increased. So we have to adjust that accordingly. So normally what happens when we grind is, so towards the mill, the wear will be on higher side. So um, that's it. So we have to replace and do it accordingly. So we'll see this. What is the minimum life of this mills, sir? So this lives, I have seen more than 40 years old, or even more than 50 years old mills also. For the ball mills, they are still running. They are running well. Hello, am I audible, madam?
Yes, you are audible. Yeah.
Because I got a message that audio is not available.
Everybody can hear? You can hear it? Please check your network connection if it is not audible. Please, I can able to hear.
Okay. So for the hydraulic roller press, the wear rate, when we see the wear rate on the liners, either let it be a vertical roller mill or the HRP, it will not be same. So after some time, the liner will start to rotate. The wear will be on a slightly triangle shape. Towards the center of the mill, the wear rate will be on higher side. So what we do is we reverse the liners so that the life can be improved well. Even for the rollers, it is the same. We reverse the rollers. For the hydraulic roller press, it's the width is higher than the vertical roller mills. So what we do is we build up the material, like we hard face, we weld it, and we increase the wear. For compensating the wear, we weld on the surfaces. We build up the rollers again so that the wear can be accompanied, and then the performance can be restored. In all the mills, when the wear rate is higher, then the performance reduces. Any other questions?
Yeah. What is the material used to make this equipments? These equipments, what is the materials?
There will be like a lot of materials, different materials. It will not be like a single material will be there. For example, the liners the liners will be mostly of high chromium alloys, and the media also of high chromium alloys. And there are different types of materials will be there. Like this grinding machinery is not only limited to the cement plant or any other things. Like these mills are very common, and in white cement, and even in for the other industries also, they use this kind of mills. So they use ceramic balls as well in some places. Some places they use pebbles, some places they use rods, and they have different mild steel will be there. And then this some center cast materials also used. So different alloys were used for this purposes. Even in some places, the tungsten carbides and other high wear resistant alloys were used. Any other question, madam?
Yes.
Yes.
How did you pack the cements with zero humidity as it plays important role in cement quality?
Yes, it's a good question once again. So the humidity is an important parameter. This cement, not only in cement, in any of the grinding. So when we see the flow sheet, wherever we have to store inside a silo. The silo will be a very huge cement structure, which capacities will be around 20,000, 7,000, 8,000. It will have a huge capacity ranges. So the material has to be stored, and then it has to come out of the silo, and then we have to pack it, and then after packing it has to be sold to the market. So that's the process. So what we have to do is monitor the temperatures. Like we have at least uh, 10 to 15 thermocouples installed inside the systems, and then we have a 24/7 running lab setup. We measure the moisture content of the input and as well as the product in every shift. Like shift is 8 hours. In a shift we measure 2 times. So we check the moisture level and then the mill outlet temperature, whether let it be a ball mill or a vertical roller mill or a HRP. The product temperatures and the moisture levels, we collect the samples, of course. So we collect the samples, uh, the representative composite samples we collected, and we check the fineness levels. Along with the fineness level, we check the moisture content as well as the temperature. So at Sempra, we also measure during the design phase or during the commissioning phase, during the optimization phase, we also check the dew point of this. So the dew point, what happens is, let it be acid dew point or a normal dew point. So we have to we maintain at least 10 to 20 degrees higher than the dew point, so that the condensation will not occur in the system. So when we are operating the mills at lower dew point levels, then the condensation occurs. Then the issues of the jamming, then the humidity. For the cement, if it is exposed to the moisture, it sets immediately. Then it is of no value. We cannot use that cement anymore. So that's the reason we check it. We do the stringent practices of checking the quality of the fineness or temperature and the moisture all the time. And then the acid dew point, needless to say. So like if we have some sulfides or the sulfur oxides in the system, then along with the moisture, if we maintain the temperature lower than the acid dew point, then it forms the acidic forms and it corrodes the system. So that also occurs. So we monitor the process temperatures and the pressures and other parameters on 24/7 basis. Any other question, madam?
We can continue. We can any questions we can ask in the last session.
Okay. So these are the three common grinding machines in the cement plant. So majorly the three equipments people prefer based on the cost, availability of the layout. For example, the land availability. If we have any issues with the land, if the land is not available, then they cannot install the equipment as we need. So for the constrained layouts, the vertical roller mill will be preferred. And then if, for example, if I have a ball mill already in my system, then I would like to upgrade the system. Then what people will normally prefer is, without demolishing the complete ball mill setup, people would like to install the hydraulic roller press system to this, and then thereby it increases the production and it lowers the power consumption, and it improves the performance of the system. And then if it is a standalone system, then people prefers the vertical roller mills as well. If based on the locations, like if I want to put up a plant in Gulf countries where I have more water scarcity, then I may not be able to operate the vertical roller mill efficiently. So in those areas, people prefers hydraulic roller presses. So these are the three common grinding machines in the cement plant, and it is not only in cement plant, it is installed in the other industries as well. So even in the aluminum industries or even the steel industries for grinding the coal, it is there. And in many other industries, wherever the grinding operations are there, these are the three most common machines in the cement plant. Madam, is there any other question, madam?
Question is that other than the feed rate constant, any other source to increase efficiency?
I'm not getting, madam.
Other than the feed rate constant, any other source to increase the ball mill efficiency?
There are other ways as well. For example, ball mill operations, not the feed actually, it is the media. Media is one part, and then the other part is like what happens is sometimes when the moisture is more and when the media, the material is what happens is the material coated over the get coated over the grinding medias, and then it reduces the grinding efficiencies. So that is one part. And in some places in recent days, and people more they prefer more they are started using grinding aid as well, like the glycol. There are different products available in the market nowadays for improving the grinding efficiencies. So the ethylene glycol, this glycol products, like they are commonly termed as mentioned as grinding aids. So people add the grinding aid to the system, and then it improves the grindability, and it improves the fineness of the product, and then that is also plays a major role. And then the other important factor is for improving the grinding efficiency is the separator efficiencies. We are seeing, since in this topic we are seeing mostly about the grinding machines, the other equally important machineries are separators. Separators, what it does is like it is not a grinding equipment, as the name indicates. It's a separation equipment. It separates the material between for example, if the ball mill, there are two types of circuit, like open circuit and closed circuit. Open circuit, what it does is we put the material inside and we collect the product directly from the outside. That's a open circuit. So there will be a limitation with the capacities and the performance. So what the people like the separator does is the mill outlet product will go to the separator. Then the separator, it separates the coarse material, and then it increases the circulation factor. Circulation factor in the sense we are regrinding the material once again, so that our fineness can be controlled. So through improving this separator and by installing a high efficiency separators, then the production and the power consumptions can be optimized as well. Any other questions, madam?
The question is actually, the main difference between facing or turning and milling and grinding.
Basic difference between?
The basic difference between facing or turning and milling or grinding.
Basically, like it is like for application purposes, basically. So they are all like, for example, when we see in the beginning of the presentation, maybe I'll show it. So they are different principles of our size reductions, basically. So the turning or the facing, like it is how the different equipments are, and then the principles are. Grinding and milling are almost like how we define it. For example, um, in different industries and different materials, people use different terms. So basically, the facing or the turning is like if we go to the if we see about this impact crushers. So this basically like this is an impact crusher. This can be called as an impact crusher, or people call it even as a hammer crushers. So that's one part. And then for the grinding machines, so grinding is basically like on the what size fractions, what is the final product. So there it will be like having a difference. This attrition processes where it is there. This can be, some people they call this as a facing also. So the attrition is the major principle here. So this is called as a grinding mills also. People, it's a grinding unit. Grinding is a common term. Mill is a particular term we use for defining this machine. Other than that, there is no such thing as like no clear definitions between these terms. It is different terms used in different locations and different processes. Any other questions, madam?
Uh, is there any grinding equipments recently developed grinding equipments available?
Um, Recently, there are like other equipments also available, but the performance wise, like there are some equipments called as a horo mill. Horo mill will be like a single roller will be there, and then the performance, and then it grinds the material. And but the performance has to be compared. So even though the ball mills and the roller presses and even the vertical roller mills, they are all established equipments. The recent trends, what people do is optimize the cost of this equipment and improve the performance of the equipments. So thereby it will be sustained on the market and it serves the purpose of this. So for the ball mills, there are a lot of developments in the stages of the ball mill. For instances, there is one question regarding the centerless grinding. So basically what it is like the ball mill. Can we see the picture of the ball mill? So maybe I will show this. So this is our typical ball mill. In the end, we can see there is a gear arrangement. This is a girth gear arrangement. And then there will be a shaft in the side. So then um, it is having the rotation is done through the side drives. This is called side drive. And then there is another variation in the mill, where in the center of the ball mill, there will be a shaft attached along with the gearbox. Then it rotates. So that is a central drive. And then this particular machine is a side drive. So there is an upgradation of this mill. And then in the olden days, people used a different type of liners. They used classifying liners, and there are different types of liners. Nowadays, people are using only the step liners. And through the cost optimized, the materials were changed. The metallurgies of the materials were changed. Then the latest developments for this is like a lot of different types of separators were launched, and a lot of separators and the separation technologies were improved. And even the vertical mills as well, there are a lot of variations in the vertical mills. For example, here we have seen a flat bottom. I will show you that. So here we are seeing the liner of the table and the roller. They both are flat. But there are other competitors and the other suppliers. What they are doing is they are having a different types of liners. Maybe that they use a bowl type liners, bowl type grooved rollers, and then this won't be a rectangular shape. People use a concave shaped rollers. So for improving the grinding efficiencies, they change the concepts. They launch new products, and then other variations will also be done. Here we are seeing about 3 rollers. In industry, there are even 6 rollers are also available for this. So for purposes, it has to serve the purpose, and the performance and the power consumption and production has to be improved. So the new products and upgrades were launched. Any other question, madam?
Any other queries from the participants? I can continue.
Okay. Are we on time frame, madam, or hello? Hello. Hello.
Yeah. Can you hear me? Yeah, almost 2 hours over.
Okay.
Check, if you finish it fast, it will be better.
Maybe we can close it now, and we'll open for the queries.
Any other queries from participant side? Any other queries? What is meant by SGM?
SG?
M.
SGI or HGI?
SGM.
Where it is mentioned?
Yeah, I'll put it in the chat box.
Are you talking about this one or?
SGM.
SGM.
Yeah.
In which slide it is mentioned?
Participant, can you mention which slide and can you mention it? Participant has asked the question.
Mm-hmm. Maybe it is regarding some slag grinding mill.
They have asked actually.
We will find it.
Okay, let's not waste time. Next question is, how is the noise controlled?
Noise is basically like the ball mill basically will have a hell lot of noise, and noise, through the noise only we control the material actually. So the for ball mill, the first compartment will have higher noise. So what we do is like we have a follow phone, like a noise meter. So if the more noise is there, then it means that the material is filled empty. The mill is running empty. So we have automatic feed control. So if the noise level is more, then we increase the feed rate. If the noise level is low, then we reduce the feed rate. So noise will be more in the ball mill. And then for the vertical mill, typically we won't hear much noise if it is running in a stable and normal conditions. If there is any abnormalities, like any roller or any liners or anything broke down, then there will be a noise. If there is any noise, we stop the mill immediately. Abnormal noise, I mean. Then we stop the mill and then we go for inspection and rectifications. But the ball mill, basically we operate with the noise, and we'll like any other mill or any other operation or anything. So we have to prevent ourselves from protect ourselves from the noise and everything. Maybe I can show you my helmet. So this is my helmet with noise enclosures. This with earmuffs. So I wear this helmet all the time when I'm inside the plant. So whenever the noise level is on higher side, I have to cover my ears and protect myself from the noise. And we put the safety signs everywhere inside the plant, wherever the higher noises will be there. There is one more question. Sir, these mills are working either atmospheric condition or isolated. So they are in atmospheric condition only, like it will be kept outside only. The way I can show the picture. Just a minute. Tell us about the centerless grinding and its advancement. So the centerless grinding, which is normally called as central drive grinding. So typically the old ones, the old type mills, they were driven by a girth gear, and through the girth gear, the mill rotates. And then recent days, or not recent, but it is also at least 15 to 20 years old. There, uh, the central from the mill will be having a center shaft, and then there will be a gearbox, and then the motor is connected to it, and then it is rotated. The advancement and the advantage basically is the girth gear. When we see the cost of the mill and the maintenance of the mill, operation of the mill, the girth gear will have more impacts, and then the cost of the girth gear will be on higher side, and we have to lubricate the girth gear all the time. And then if there is any problem, if there is any crack or any damage in the girth gear, then the whole plant or the mill has to stop for months together. So even people don't like to keep the spare of that. It's a very high cost equipment, so people may not keep the spare as well. So there, the central drive will have that advantage. Without the girth gear, it can operate, and then it runs well. So that's the advantage. And answering to the previous question, um, atmospheric condition or isolated. This is, as we can see, it is in the atmospheric condition only. But inside the mill, it will have their own setup. Like here we can see the duct. This is a hot duct. Hot air entry will be there. Then the mill, inside the mill, the temperature will be around The inlet of the mill will be ranged from 200 to 400 degrees Celsius, and then the mill outlet will be 80 to 98 degrees Celsius. So the suction will be higher because the material has to be lifted throughout the mill and it has to be taken to the separator. So as high as 1000 water column pressure will be maintained inside the mill. Any other questions, madam?
Say something about the storage tanks of cements. What's special in it?
Yes, that's another interesting question again. So maybe I can show the pictures of that. So the cement, not only the cement, even the fine grounded material, let it be a raw material or even the coal or even the cement, they are stored um, inside the silos. The silos, maybe I'll show the pictures of that. So it is, these are all specially designed equipments because what we do is we need to homogenize the material. We have to store it for a longer time, and then it has to serve a lot of purpose. First, it acts. We need to store for the purpose of the silos is for storage. For example, if I would like to have a maintenance of the mill, I cannot stop the other process for that purpose. So I need a sufficient quantity of material to store enough to store the material. So that is storage is one part. So the material has to store inside this silos and it has to be homogenized as well. And then it has to deliver the material as well. So it should be it how to say that it should serve all these three purposes: storage and homogenization, and as well as flowing of material. So maybe I'm taking one more presentation of that. So the silos, let me see. So these are all specially designed equipments. Maybe I'll show this one. Okay. So here we can see this silo. First is this raw mill silo, and then it is a cement silo. Here we can see there are 5 cones totally, and here we'll have up to 7 cones will be there. So it will be aerated continuously. So through the blowers, we aerate this material. We keep on blending the equipment. So through the blending, we keep on blending the material, and we ensure the free flowing of the material, and we extract from this 5 cones. We extract from each side at once. So there will be ratios. So we take from different ends all the time, so that the metal homogeneity can be ensured, and also the temperature inside and the pressure is also maintained. And then here we maintain sufficient draft so that the metal will not form a cake inside this silo. So it will be continuously aerated. So these are all specially aerated designs. And for the cold mill, we have either inside, like the setup will be smaller because of the ignition properties of the coal. So we have either nitrogen purging or CO2 purging. In case if ignition occurs, so we use the nitrogen, we purge with the nitrogen or with the CO2, so that the fire, the ignition source can be controlled. Does that answer the question? Is there any other question?
Another one question. Again, they're asking: is it necessary to put the feed in SGM before it is done in your ball mill? Why it is?
Uh, I'm not getting any. I'm not getting clear.
Okay, maybe they have asked from Google. They have asked actually it is necessary to put the feed in STM before in ball mill. Whether it is put in STM before it is sent to the ball mill. Why this?
Not necessarily, actually. Like here, when we see this flow sheet, for example, here in the raw mill, it will not be in. We store it actually. We store, for example, here we have 4 different materials: limestone, clay, sand, and iron. So these all stored in a different tanks. Then we have a weigh feeders, weighing arrangement for each of the material. So we take in a ratio and like different ratios for our maintaining our quality. So for that quality purpose, we store it and then we convey it and then we directly feed to the ball mill. So there won't be any other intermediate between this. The material can be directly stored, directly fed to the ball mill. Or maybe if the sizes are higher, maybe they are mentioning about the small grinding mills. Maybe SGM is that small grinding mill. Maybe it is required because the size, if it is a small grinding mill, then it is required because the mill cannot handle, for example, when we quarry, in the quarry, the material will be as high as 1 meter, or even you can see 2 meter high material. So we cannot handle and feed the material that high, the big boulders to the mill directly. So the mill, as we say in the presentation, let it be a ball mill or a vertical mill or a roller press, the feed size is an important parameter. We cannot put a direct quarried material to the system. It has to be pre-processed. So the pre-process here is the pre-grinding. When we see like the pre-crushing, we should call it as a crushing. So the metal has to be crushed enough, or even it can handle up to 100 millimeter, or even 150 millimeter to some bigger size mills. So that crushing has to be done. Then it has to be fed to the mill. So that's how the system is. Any other question, madam?
Any other questions, participants? Can we close the session? Can we close the session, sir?
I don't have any issues. If the things are clear, maybe I'll share the presentation to you.
Yeah, PPT.
So that will be helpful. So I'll share it, and in case of any queries, I can be reached anytime. I'll share
Post
my.
it to you. Yeah, definitely.
I'll share my contact details to this.
Okay. I think there is no queries. Now I request Mohammed Bilal of final year to deliver the vote of thanks.
I have shared my contact details through the chat. You can access it.
Ma'am, can I start?
Yeah, you can start.
I, Mohammed Bilal of Final Year Chemical Engineering, is here to propose the vote of thanks. I extend my gratitude to our management, to our principal for their continuous support in organizing this event. I am thankful to our dignified speaker for giving us an elaborate presentation on grinding technology and their usage in cement industry. I would be grateful to our HOD for arranging such a learning session in chemical engineering. I am very thankful for our coordinators, organizers, and staff members for their constant support. I express my gratitude to our participants for being in day 2 session. I once again thank you all for your very presence in our learning sessions. Thank you.
Thank you, Bilal. Announcements to all the participants. Tomorrow we have session at 11:30. So stay back, and for further notification, you can see the WhatsApp group. Okay. Thank you very much, Mr. Sendil Kumar, for your presentation and sharing all your views on your latest trends in your grinding technology. Thank you very much for your acceptance of the invitation. Also, thank you very much.
Thank you.
Dear Sendil sir,
Thank you.
hello.
Yes, sir.
Dear Sendil sir, thank you so much. You've given a wonderful presentation. It will be what more interesting as well as what more informative, right? Really, I'm very wondered about your presentation. Okay, and the way of your presentation is also really very enjoyable. And then our students are also asked a lot of questions. It means that you have impressed them like anything, right? So really, thank you very much for your presentation, and also you have immediately accepted our invitation. Thank you, sir. We're also expecting the same kind of support from you in future also, sir.
Anytime, sir.
Thank you so much. All the very best, man.
Thank you, sir.
Thank you. Yeah.
Thank you. Okay, sir. I'm doing it.